morning, Integrated Topics students. Ms. Codner here for April the 4th. Today's lesson is a combination of March 31st, April 1st, and also for April the 5th. The reason why we got the breakup because we had the special schedule early dismissal on Thursday, March the 31st, and then only had so many people that were able to do what we need to do for March the 1st since we were doing an activity last class. So I just decided to basically go through the whole entire lesson from the 31st over to April the 5th, so everyone won't be missing bits and pieces here and there. So we didn't have any homework the night before, so what we're going to need for today is pencil, calculator, loose leaf paper for notes, and also an open mind ready to fill with knowledge. Yeah, very deep, but we definitely need some knowledge today. So we're going to get started. So today's topic is factors and the GCF, and I'm going to turn this volume up so you can hear me a little bit louder. How's that? Okay. So we're dealing with factors in the GCF, and what I mean by that is when two or more numbers are multiplied, those numbers are called factors. So for example, we have 90 and we have 36. So if I wanted to take two numbers multiplied together to give me 90, what would those numbers be? So some students told me 9 times 10. Some will tell me 3 times 30. Also, I had 2 times 45. Some were clever enough to tell me 1 times 90. And all these are reversible. So if you think 10 times 9, that's the same thing. And let's say 5 times 18. Okay, and there's probably a couple more. So we just basically got these, and these are the factors for 90. So 9 times 10, that's a factor for 90. 3 times 30, those are factors for 90. 2 times 45, the factors for 90. And also I can use negative numbers. So if I wanted to say a negative 18 times a negative 5, those are also factors for 90. Okay? So now skipping over to 36. So many right away said 6 times 6, 1 times 36. We got 12 times 3. What else gives me 36? How about 4 times 9? Okay, so these are the ones that I can figure out the top of my head. And there's probably a couple other ones. I think I have 3 times 12 up there. Yeah, how about 2 times 18? Put that up there as well. So again, 6 times 6, those are factors of 36. 1 times 36, and also vice versa, those are factors of 36. So basically, two or more numbers. So if I wanted to go with the factors itself, it will be 1, 2, 3, 4, 6, 12, 9, or 9, 12, 18, 36. They're all factors of 36. So once we got the understanding of what the factors are, we wanted to talk about two different types of numbers. So the first type of number is called a prime number. So what the prime number is, it's a whole number greater than 1 whose only factors are 1 and itself. So I know there's an infinite number of prime numbers, but what will be the first prime number? So a lot of people told me 1. 1 is not the first prime number. It's actually 2. Okay, so think about it. When we're dealing with 1 and itself, that means we're constantly using that number 1. So if we're constantly using that number 1, it's no way that it can be prime. But if we think at number 2, are there any two numbers other than 1 and 2 multiplied together could give me 2? No, there isn't. So every time you think about this, you may see this on SAT questions. You may also see it on ACT questions, college entrance exam. They may ask you to use the first set of consecutive prime numbers, and a lot of people always make the mistake of using 1. So your first prime number is always 2. What's another example of a prime number? We can say 3, we can say 5, 7, and a lot of people always want to tell me 9. Why? Because you're finding a pattern, right? But is 9 a prime number? No, it's not, because I can do 3 times 3 and I can do 1 times 9. So that's not a prime number. But 11 is, 13 is, 15, definitely not, because I can do 5 times 3. But 17 is, and 19 is, and if I wanted to go a little bit further in the 20s, also the number 23. So a lot of people notice that prime numbers are mostly odd numbers, except for that number 2. So number 2, in this case, is the only even prime number. Most of the other prime numbers are odd, but you have to be careful. They're not all odd numbers. I don't want to say that, okay, all odd numbers are prime. No, because 15, that's not a prime number. 9, that's not a prime number. 27, that's not a prime number. But those 3 numbers that I mentioned, they are odd. Okay, so make sure you get that clear. As long as it has its factors that are 1 in itself, will be considered a prime number. So after prime, we talked about composite numbers. So a composite number is a whole number greater than 1 who has more than 2 factors. So we mentioned a few examples of this before. So we can say 4. And the reason why 4 is a composite number, because I can say 2 times 2, and I can say 1 times 4. Another one would be, let's say 24. And with 24, I can say 1 times 24, and I can say 2 times 12, 4 times 6, okay, 8 times 3, okay. So you can see this has about 2 factors, well, really 3 if I count 1, 2, and 4. And this one I can use 1, 2, 3, 4, 8, 6, 12, and 14 as factors. So since I have more than 2 factors and I have a whole number that's greater than 1, that means those 2 examples there are composite numbers. So just to test out to make sure everybody knows what they're doing, we want to find the factors for each number, then classify each as prime or composite. So starting with number 1, the number 52. So what are my factors for 52? So I know right away a lot of people told me 52 times 1 because it was easy. And the other one would be 2 times 26. We can use that. And we also can say 4 times 13. And let me stop right there. So now I definitely have more factors other than 1 in itself. So it can't be prime. So in this case, 52 is a composite number. For number 2, we have 20. So we can say 1 times 20. We can say 4 times 5. We can say 2 times 10. So we have more than just one set of factors, that 1 in itself. So this is also a composite number. So how about number 3, 31? And I know I'm kind of going through this quickly, but if you want to pause, you can pause it and try to work these out. So for 31, this would be considered prime. And the reason why it's prime, because only 1 times 31 will give me a product of 31. There's no other numbers other than 1 in itself that can multiply to give me 31. Now, 112. So I know I can do 1 and 112. I can do 2 and 56. I can do 4 and 28. And I think 8 and 14. So we'll stop right there. So again, they're interchangeable. So since I have more, so this is also a composite number. And lastly, number negative 72. So right away, you're going to be like, oh no, it can't be prime, it can't be composite, so it's nothing. But careful, we still can make factors of negative 72. So what would be some factors? I can say negative 1 times 72, or vice versa. I could say 1 times a negative 72. I can say negative 8 times 9, or negative 9 times a positive 8. How about 36 times a negative 2? That also gives me a negative 72. And I think the 12s. Oops. 12 times a negative 6, or negative 12 times positive 6. So I still have factors that can represent my negative 72. But when it comes to the classification of prime and composite, I would have to say it's not classified, or it's neither prime nor composite. So I know as soon as you see that negative number, because as we said, we definitely have more than one factors. It is a whole number, but it has to be greater than 1. So that eliminates negative numbers and it eliminates fractions. Okay? So since it doesn't satisfy that, and it's neither, if I may flip back sometime soon, okay? It also doesn't satisfy the definition of prime numbers because it's not factors of just 1 in itself. We also proved that. Okay? So we can still find factors of numbers, but when it comes to classifying if it's prime or composite, you have to follow with your definition. A, it has to be a whole number. B, it has to be greater than 1. Okay? So after we looked at that, I wanted to touch on prime factorization. Now, prime factorization you have seen before. I think a lot of this you've seen before. But if you remember, back in the days of elementary school, when you dealt with the factor tree. So meaning, I have 2 examples here. I have example number 12 and also have example number 90. So I want to think of 2 numbers multiplied together to give me 12. So I can use 3 times 4. I could have used 6 times 2. I know a lot of people want to use 1 times 12, but if I want to factor things down, I don't think I want to use 1 times 12 because guess what? It's taking me right back to the very beginning with the 12. So what our ultimate goal is with this prime factorization, we want to take that whole number of 12 and we want to find factors that multiply together that are all prime numbers that is going to give me my original answer of 12. So looking at 3 times 4, this 3 is a prime number, so it's staying right where it is. But this 4 is a composite number. And we can actually break that down again, which will give me 2 times 2. So again, 2 is a prime number, and 2 is a prime number. So if I wanted to rewrite this as a prime factorization, I would go 2 times 2 times 3. This is going to represent the prime factorization of my original number 12. So if you wanted to check it, you can go 2 times 2, which is 4, times 3, which is 12. So we're trying to break this down until we get all prime numbers. Okay? So looking at 90. So for 90, we can start any which way. We can say 3 times 30. We can say 9 times 10. We can say 45 times 2. It doesn't matter which set of numbers you start out with. No matter what, your prime factorization is going to be exactly the same. So let's just say, oh, I don't know, 9 times 10. So that means 9, that's a composite number. So that can be broken down to 3 times 3. Let me put the plus sign or multiplication symbol there. So I can bring the multiplication symbol there. And then 10 is also a composite number. Last time I checked, it was 5 times 2. So now 3, that's a prime number. 3 is a prime number. 5 is a prime number. And 2 is a prime number. So if I want to arrange this in numerical order, starting from least to greatest, I can go 2 times 3 times 3 times 5. So this is the prime factorization of my original number, which was 90. So check it. 2 times 3 is 6. 6 times 3 is 18. 18 times 5 is 90. All right? So that's what we're doing with prime factorization. So let's go with another example. We have a negative 16x cubed. So we have a negative number. Now, you're still doing the same exact thing with the factor tree. So my suggestion is take care of the number first. So we have a negative 16. And just like we said about a prime number, it has to be a whole number and it has to be greater than 1. Right now, it's not greater than 1. But what we can do is factor out that negative 1. So I'm pulling out that negative 1 so I can get 16 in its positive frame. Because negative 1 times 16 gives me an original negative 16. So now from here, I can factor that 16, which I can get 4 times 4. And then these 4s I can factor, which is 2 times 2. And I have 2 times 2 on the other side. So now, that negative 1 is over there. The negative 2's there, negative 2, and negative 2. So numbers-wise, I have a negative 1 times negative 2 multiplied by itself 4 times. And I know a lot of students are like, well, Ms. Conner, can I just simply just write 2 to the 4th power? That's fine, but we're doing prime factorization. This is going to help when we actually do factoring. So I know it seems like, oh, there's a shortcut. Yes, but I'm doing all this to help with the next step. So now we took care of the negative 16. Now we need to take care of our x's. So we have x cubed here. And x cubed is just another way of saying that I'm multiplying my base of x, remember that from exponents, to itself 3 times. So since this whole thing is being multiplied, all I'm basically doing, don't want to bring all that, just want my x's. All I'm basically doing is taking my x's and putting them with my numbers. So now I have a negative 1 times 2 times 2 times 2 times 2 times x times x times x. This right here is the prime factorization of my original negative 16x cubed. Do you see how it's going? So we break down the number, then we just break down the variable. It's just telling me how many times I need to multiply my variable. So let's take a look at this one. So we have 30m cubed n squared. So if you want to pause this so you can do it by yourself, go ahead. Okay. For a 30, I could break down this 30. Let's say 5 times 6. Okay, so this 5, prime number, but this 6 is a composite number, which also can be broken down by 2 times 3. So if I want to put it in numerical order, I'll have 2 times, oops, 3 times 5. So that's dealing with the numbers. Now I have to deal with my variables. So I'm going to times my m to itself 3 times, because that's what the cube's representing, times my n twice. This right here is the prime factorization of 30m cubed n squared. So 2 times 3 gives me 6. 6 times 5 gives me 30. M times m gives me m cubed. And n times n gives me n squared. Okay? So then I had the students try these 3 on their own, just to make sure that we're all on the same page, making sure that they understand the concepts. So with this one, we have 48a squared. So thinking of the 48, we can do it 6 times 8. You can do it 12 times 4. You can break it down any which way you want to. So in actuality, if I do it 12 times 4, that means I'm breaking down that 12. Okay, I can break it down 6. So then that 6 will give me 2 times 3. So I'll have 2 times 2 times 3. And then my other 2 2's. So in actuality, I have 2 times 2 times 2 times 2 times 3. Okay, 2 times 2 is 4. And then my other set of 2 times 2 will give me 4, so that's 16. And then 16 times 3 will give me my 48, times my a squared, which is a times a. For the next one, 12xy. So we have our 12, which could be 4 times 3. So that will give me 2 times 2 times 3 times my variables, x times y. And lastly, so this one, and try to drag it down a little bit, really going to need a little bit of room. First off, it should be my negative 1. So with me pulling out my negative 1, I know I'm going to have to multiply 2 to itself 5 times. And I got 5 2's there. So 2 times 2, 2 times 2. So we have 16. Then 16 times 2 gives me my 32. And I have my negative to represent my negative 32. Then I'm bringing my x's down. Times x times x times x. Now I got y squared, which means I have to multiply y to itself twice. Okay? So if you're not sure, check how you do it. Okay? So all you're doing, you can do the factor tree just to break all this stuff down. And that's basically what we did. I gave them a good 5 to 7 minutes. And a lot of kids were basically done before that. Okay? So that dealt with factors. Okay? So breaking it down all the way to the bare bone, which is the prime numbers. But now we're going to go into the greatest common factor, GCF. So what the greatest common factor is, we're basically finding out what number do those factors have in common. So it's almost like looking at a needle in a haystack, hence the picture. So for example, we have 12 and we have 16. So I like to do this by examples. So if we took what we just learned, if I wanted to factor out my 12, I can do 4 times 3. 3 is going to be a prime number. That means I can break down my 4's, which is 2 times 2. Okay? So if I wanted to, 12, if I want to say it's equal to 2 times 2 times 3. Okay, that's the equivalent of saying 12, but all the way in its prime factorization. So I'm going to do the same thing for 16. So here I have 4 times 4, which is 2 times 2 times 2 times 2. So for the 16, I have 2 times 2 times 2 times 2. So once I factor both of them out, what do you notice? I notice that they have this group of 2's right here in common, and they have this group of 2's right here in common. The 3 and the other 2's, right now, that's not what's left in common. So if I wanted to state what is my greatest common factor, I would say the 2 from the first grouping times the 2 from the second grouping is going to be my GCF, which is a total of 4. And as stated in class, when I look at the 12 and 16, some people might see it right away. Some people noticed it right here, that they both had 4 in common. Some people originally looked at it and say, oh, they have 2 in common. But I wanted to know the greatest common factor. So you can do it this elongated way, or if you notice it right away, you can do that as well. You know, I'd rather you do it the way that you understand it. Okay? So all I did was get the prime factorization of 12, and then got the prime factorization of 16, and I just circled what they had in common. They had 2 2's in common, so that means I'm dealing with this 2 and this 2. And I'm multiplying those 2 together. Hence, I got 4. Let's try the next one. 27 and 72. So what would be my greatest common factor? So we can do it this way. 27. I have 9 times 3. And my 9 is a composite number, so I factor that out again. So 3 times 3. So for 27, my prime factorization would be 3 times 3 times 3. So now looking at the 72, I can say 8 times 9. So for the 8, I can factor that out to a 4 times 2. So there's my prime number. That means I have to factor that 4 out again. Ooh, not 4. Let's try this again. Got 4 on the mind. 2 times 2. And then for the 9, I'm factoring that out, and I got 3 times 3. So let's circle all my prime numbers. So if I were to rewrite that 72 as a prime factorization, okay, I'm going to just do it in numeric order. So I got 2 times 2 times 2 times 3 times 3. What do you notice? Well, I notice right away that I have one set of 3's and they have another set of 3 in common. Yes, they're not lined up, but we're not looking for what's being lined up. We're looking for what they have in common. So they have 2 sets of 4's in common. So that means I have 3 times a 3, 3 from the first grouping, and this 3's from the second grouping. So that means my GCF is a total of 9. Okay? And again, a couple of my students later on said, hey, I noticed that the 9 repeated here from the very beginning. Very good. Okay? So if you notice it from the very beginning, again, go with it. That's probably your greatest common factor. But if you're not too sure, you can do it this way, just so you can keep everything in line. Okay? So now you can try number 3. If you want to, you can pause it. And we'll check our answers momentarily. So for this one, number 3, we have 18x. So again, we're going to do it just like how we did the other ones. So first off, deal with the 18. So you can say 9 times 2. So that means that 9, I'm going to factor 3 times 3. So here's my prime numbers. So then for this 18x, my prime number is going to be 2 times 3 times 3. And now I'm looking at that x, and since there's only one x up there, it's going to be times x. Okay? So now with the 30, again, you can use any numbers. You can use 3 and 10. You can use 6 and 5. You can use 15 and 2. You're going to get the same answers as your prime factorization. So again, I have 5, 3, and 2. So let me write this down here. 30x squared. So this will give me 2 times 3 times 5. And now how many x's do I have up there? I have 2. So it'll be x times x. So they're both now broken down, their prime factors. So what do you notice? They have a group of 2's and they have a group of 3's. Anything else? Yes, they have a group of x's. So now my GCF. So since I have my 2, which is from my first grouping, times my 3, which is from my second grouping, and times my x, which is in that third grouping. Okay? So now 2 times 3, last time I checked, is 6. And since I have 1x, I have 6x as my greatest common factor. Okay? So usually about here, that's when a lot of people are like, oh, I totally get it. Okay? So of course, I have a couple more examples. So don't be fearful of it. So it's 20gh and 36g squared h squared. So think of your numbers. So if I break it down, I'll have 2 times 2 times 5 times g times h. If I break down this 36g squared h squared, so I'll have 2 times 2 times 3 times 3 times g times h times h. So remember, 2 times 2, 4. Okay, 3 times 3, 9. 4 times 9 is my 36. What do they have in common? So what they have in common are this group of 2, another group of 2, a group of G's, and a group of H's. Now, I didn't say it was going to be pretty, but what is my greatest common factor? So it's my first group, which is my 2. So that's for my first group. My second group, which is the other 2. It's my second grouping. Then we have my G, which is from that third group. And then lastly, I have my H, which is from my fourth group. You can have a multiple amount of groups. Okay? You can have a multiple amount. You can have 6 groups. You can have 4 groups. There's times you might just have one thing. There may be times you may have nothing in common. Okay? Just like a relationship. I'm just kidding. So now, 2 times 2 will give me my 4. Since there's one G and there's one H, my greatest common factor is 4GH. Okay? So, last example. Yeah, we had a lot of notes for this class. So I gave them the chance to do this. So we have 42, we have 60, and we have 78. So we don't have any variables. You could break it down just like you did. I can actually give you a moment to try for you to figure out what number do 42 does, I should say, does 42, 60, and 78 have in common? So hopefully you said your greatest common factor is 6. Let's think about it. We have 6 times 7 will give me 42. We have 6 times 10 will give me 60. And we have 6 times 1, 13. They all have 6's in common. You could have done the factor tree, which will break down that 6 and 7. You can do the factor tree, which break down the 6 and 10, and also for the 6 and 13. But no matter what you've done, all of them have this lovely number 6 in common. Okay? So I forego this last part because it seemed like a lot of people had that practice. But this was the homework assignment. And this homework assignment was given to the students for April the 4th and also for April the 5th. So again, there was no homework on the 31st of March nor the 1st because we didn't really get all the way through to this lesson. So this was their homework assignment for the 4th and the 5th. These are 5 problems that are on the board. So for problems 1 and 3, they just had to do the prime factorization. So it's almost like they could just have to do the factor tree and then circle their prime numbers. They could have done it that way, or they could have basically put all their numbers in numerical order doing multiplication, just like how we have been doing in this lesson. And problems 4 and 5, they're going to find the GCF. So yes, you can do the factor tree, but I want to know what is the greatest common factor for 24 and 81, and what is the greatest common factor for 18a and 48a to the 4th. Okay? So other than that, that's what we did for today, and that was the assignment for this evening. If there's any questions, you might want to replay it. You can replay this lesson again. And also, I'm available Tuesday, Wednesday, Thursday during Wildcat Hour in room C107, which is my classroom. And also on Friday, Ms. Cabanallen is in my classroom during Wildcat Hour as well. Okay? So let's start off that 4th quarter on the right foot, and let's get this